Hello everyone, welcome. This is the first chapter in our course. We are starting from we are following the Hibbeler slide and we are continue from the chapter 8, combined loadings. Also, this chapter helps us to review all the stress types, also how we can calculate this stress, also help us to figure out and to remember. Okay, let's continue. I'm sorry. Okay, you maybe remember from the strength of material one. We divide two type of stresses at two type of stresses occurred on the infinitely small element of our body. We call this the shear stress. Shear stress is the stresses occur to perpendicular of to parallel to surface. If your stresses is parallel to your surface, like you and this one, okay, we called is the shear stress. Maybe you can see I didn't define any subscript on tau. You can see on the figure y and x notations. Maybe I can explain. Y represents to surface notation, x represents to direction notation. So tau yx meaning that on y surface, because in this surface is perpendicular to y direction, also to x surface is to parallel to the x direction. Therefore, we call this tau yx. And you can see the stress is parallel to the up surface. Also, this surface, I can call in this action also, I can write the axis in here. And this axis is the x-axis, okay. This is the y-axis, okay. This should be an z-axis, like this. So we can see this surface on y-axis, x-axis, okay. Therefore, we call this x notation in here. Also, direction on y. Therefore, we called in tau xy. Now you don't need to learn to how we can write the notation, but in chapter 9. Maybe we need these definition. Therefore, if you get used to like this definition, that can be helpful for you for 3D surface. Okay. And second type of stress, also you can see normal stress. It's a good thing that I can clear this part. Sorry. How can change? Yes. Second type of stress is the normal stress. In normal stress is direction in perpendicular to the surface. So there's only one notation on sigma, okay? And you can see sigma x as direction is perpendicular to surface x. Also for equilibrium, this direction also should be in sigma x. For example, this direction we can call this sigma y. Also, down direction also available for sigma y. Also, this direction is sigma z. Also, we can call this in direction is sigma z. I am not sure it makes you confused or not, but maybe I can explain like this. We define all stress by 3x3 matrices. Okay, for example, we can call for diagonal direction, we can call sigma x, sigma y, and sigma z. Okay, in here tau xy, tau xz, okay, and also tau yx, okay, tau yz, and this one is tau zx, tau zy, okay. like this. In some books, maybe you can see to x-axis, sigma x-axis, sigma y, and sigma z. Sometimes they define in only one notation. Remember that this is the surface. This first term is represent surface. The second term represented the stress direction. Also, in maybe if you also if you look at in different books and if you see like this representation, okay, don't be confused. Okay, this is the vector representation. Okay, I'm sorry. I'm having a trouble to open. Yes, I can clean it. Okay, I can pass to the next slide. Okay, we can categorize how to normal stress and shear stress occur, in which type of resultant forces causes type of stresses. First of all, we start with the normal force. In chapter 2, maybe remember that if you look at in chapter 2, you can easily figure out if you have a, for example, things like beam or column like this. Okay, if you put to axial load P like this direction, okay, to the normal stresses. And normal stress, we also, you remember that we define as a sigma. The value of the normal stresses is equal to normal force divided by the gross area, also standard area, not net area, sorry. That also I can show you in here. Normal stress occurred on surface on the body. This direction is force direction, is the tension direction. Therefore, normal force like is the tension along the whole surface. We have a constant sigma value, and also this sigma value is equal to P times divided by area. Sorry. Like this. Okay, maybe we can pass to the next slide. Okay, if we have a shear force, you remember from static, okay, shear force causes the shear stress. How we can compute the shear stress? The formulation, maybe from chapter 7, you can figure out. Shear stress formulation is tau, we represent as a tau, you remember from the 2 slides before, is equal to V times Q divided by moment of inertia times T. I want to explain this term. V means the shear force. You can obtain from the static force. This is the input value. Q is related to our section moment of inertia, area moment of inertia. In general form of Q is equal to, also you can find the details from the chapter 7, just only I want to summarize the formulation, is equal to, for example, in like this surface, and I am looking for the y direction on tau, not x direction. So in order to calculate the tau y direction, and Q is equal to y times the A to area. It's very close to the moment of inertia formulation, but formulation is a little bit there is only one term, not y square. Y is available in that term. And you know, integration seems to be complicated, but if you have a, for example, have a rectangular surface or like a non surfaces, calculation of TQ is a little bit simple. I want to use a different color like this. For example, this is the natural axis, okay, and we are like choose a like point, any point I want to define as a point C, and I want to measure to I want to compute Q on point C, okay. Q C is equal to area C times Y bar C. What is the area C? You can see area C is equal to B times, okay. Also, I want to whole part is, for example, this is H over 2. I want to regular shape. This is the H over 2 at the middle of the beam. Okay, B times H over 2 subtracted. I want to call this term as a YC. Okay, YC. Okay, this is the AC times Y bar C is the, this is the centroid of the shaded area. Okay, this is the Y bar C. Also, we can compute, you know, H over 2. I think that can, no, it's okay. H over 2 minus, I think it's a more simplification in here, sorry, minus, this term is H over 2 minus YC, so H over 2 minus YC divided by 2. Okay, it seems to be formulations, it seems to be complicated, but if we have a numerical terms and calculation of QC is easier. Also, you remember that the I is the moment of inertia. You know, the general form, the moment of inertia is equal to, for example, for x direction, yx is equal to y squared multiplied by dA. You remember from to, if I have a rectangular cross section, if I have a calculated to ix, and if I say the width of the cross section as a b, height of, if we define the height of the cross section as a h, ix is equal to, you remember that, I think that b times h cubed divided by 12, like this. It seems to be complicated, but not complicated. I think that you can remember these formulations from the strength of material 1. Just only one term remaining. T is the thickness. For example, in this section, thickness is equal to width of the beam. We can call it as a B for rectangular cross section. I want to erase all this thing, and I can pass to the next slide. If we have a bending moment, our formulation changes. For bending moment, normal stresses occur. Normal stresses occur. How we can do normal stress? By using this formulation. Sigma is equal to m times y times, m times divided by I multiplied by y. What is this definition of these terms? You know, m is the moment, I is the moment of inertia. I explained the previous slide. What is the meaning of I? Y is the, for example, if I'm wandering from the sea, you can see y is the distance between the point to natural axis. This is the natural axis, okay? This is the point C. So y is equal to, for this point, you know, if the C is going to the upside, you know, the stress increases. If your point is close to the natural axis, your normal stress decreases. If I want to draw a normal diagram, a normal force diagram due to the shear force, it's easily you know, there's a, if the moment is constant, also we have a to moment of inertia constant. Therefore, relationship between two normal stress the y have a linear relationship. Therefore, our relationship is the linear. Okay. So to I want to explain to just only I want the upside and the compression. Okay. Downside in the tension. Sorry, like this. It's up to direction of moment. For example, in order to make an upside in the compression and the downside in the tension, moment direction should be like this terminology. Okay, and you can see the maximum stress can occur to top and bottom parts of the cross section, and on natural axis sigma bending on natural axis, sigma bending is equal to, is equal to 0. On natural axis, the normal stress due to the bending moment is equal to the 0. You know, this terminology, I thought you already know these terms. I am explaining the stresses in order to remind you, in order to remember. Okay. Also, one term is remaining. If we have a torsional moment, actually torsional moment for two circular shapes, not only to other type of shape, because torsional moment causes both shear stress and normal stresses, but unfortunately for normal stresses calculation of due to the torsional moment a little bit complicated. We call this a warping effect. You are not responsible. There maybe your instructor Uğur Hoca, I think did not tell you about the warping effect. It is the like the master class, master science level type of stress, because you are not responsible. Maybe you told about the circular shape. In circular shape, for example, if I have a circular shape, for example, if we're wandering to stress and light point C, this is the centroid of the R circular shape. Distance from this point to centroid, we call this rho. Sorry, like this. I hope you like rho. Okay. So if I also we have a like to torque value, we call this a T. Okay. If we want to do shear force, so you know shear force is I can say parallel to the surface. Maybe I can use the how to what is the direction. Maybe I can help you. Also direction of the shear force like this, small. Okay. This icon is a toe. Okay. And toe is equal to team torque times rho. Rho is the center distance between the center to needed point. Okay. J is the moment of inertia. Which moment of inertia? Polar moment of inertia. How we can compute the polar moment of inertia? I want to say the R squared J is equal to R squared times dA. What is the, how we can calculate R squared? Maybe from the, remember from the polar coordinate system. For example, if we have a like coordinates X and Y, and therefore like this is the radius. So if I compute to R square is equal to X squared times Y squared. Therefore, if you want to compute to do J is equal to IY times IX. In other words, if you know to moment of inertia on y-axis and x-axis, polar moment of inertia summation of these moment of inertia. Okay, ix times iy, just it, not complicated formulation. Okay, I think that I showed you all terms. I think that these figure is not related to this. I think I should raise this part. Okay, I should use a different shape. Okay, now we finished to summarize of the stresses. Now we will find to do resultant stat. In other words, combined loading, total stress. How we can combine the total stress is, I think that the methodology is very simple. Which type methodology we are using? We are using the method of superposition. What is the meaning of method of superposition? The method of superposition is, if your structure has a linear behavior, okay, we can divide our loadings or internal effects, okay, and we can solve separately each effect, okay. After solving, our solution, summation of whole solutions, okay, is equal to the summation of the whole effect. Therefore, in other words, divide, solve separately, and combine is equal to the combined solution. Therefore, it is very easy way, okay. So how we can apply how we can apply the method of superposition to obtain resultant combined loadings? First of all, we separate our loading or our internal force. Axial, for example, we have an axial load, bending, torsion, or shear. Okay, we separate the axial loading, bending moment, torsion, and shear. Then we try to find stresses from this loading. Also, biaxial loadings. Also, you have, for example, if I have a bolt moment on x-axis or moment on y-axis, also we can divide, okay, moments. Then we calculate two normal or shear forces from this loading due to this loading, okay. I already told in section 8.1 how we can obtain these shear forces, or sorry, these stresses. Then after that, we obtain to all type of the normal forces and shear forces. Also, we consider on the direction. For example, one of is tension, one of is compression, one is going to the upside, one of two shear force type is going to the downside. Okay, we categorize. Then we combine vectorial component as a vectorial component. Okay. Then after summation, we obtain the real value. Okay. Resultant value, and this is the result of our problem, our example. Okay. The best thing that to start with the simplest example. Not simpler there. Maybe we can have a much more simple example, but this one is the good one. This is example 8.1. You can take this example from the Hibbeler 9th edition. Maybe different edition you have a same example. I don't know following to the later versions. Okay, it's up to you, and it's a very simple question. I said. Okay, let's start with the reading the example. Point force is applied to at the top of the column. Okay, the value of the force is the 15 kilonewton. Okay, in the question needs to determine state stress, resultant stresses, in other words, on point B and C, like these points. Okay. First of all, we try to find the internal effects on point B and C. How we can compute? The best thing that, okay, take a cross section and write the equilibrium equation and find it. This is the exact way, the most corrected way, but I know you are an engineer, you took the statics, you took the strength of material. We don't need to spend time to find it, Okay, it is easy to, if you want to carry to, this is the main point, okay? We have two effects. First of all, to forced effect. You can see 15 kilonewton, the compression, okay? Also, these force, there's some kind of eccentricity in here, like this. And also that causes the moment. How we can find this? Force times eccentricity. What is the eccentricity? 50 millimeter. If we multiply by this, we obtain the moment. Hocam, why in the book they are taking this section? Hocam, can we do this like this? For example, if first surface like going to the up surface, okay, we can move to the 15 kilonewton like this, okay. And if we choose the moment like this, and if we say like point B and C like this, okay, this illustration is also correct. You will obtain same result. Okay, it is up to us. Okay, if you have any trouble to how we can find to the direction of the moment, okay, you can ask as a comment. Okay, I will explain. Let's continue. So in this surface we have a compression, axial force. Also we have a 250 bending moment. In order to obtain the in order to explain as a megapascal, therefore I need to unit transformation from kilonewton to newton, from kilonewton to millimeter to newton millimeter. Okay, I think I need to clean this part and pass the next slide. Sorry. Okay, first of all, start with the axial load. You remember I want to take a cross section like this. I'm using the different type, like we have a 15 kilonewton. We don't need to consider the moment right now. We have a 15 kilonewton. We, remember that there's axial force. Formulation axial force is P times area. So we have I already converted to from 15,000 Newton divided by what is the area dimension. Look at the dimensions. You can see 40 millimeter times 100 millimeter. We are working the Newton millimeter, don't forget. Okay, 100 times 40, we obtain to 375. You can see I didn't put the positive, negative things. Then I write to the direction using to do compression or tension. Okay, this is the strategy. Okay, sometimes you can follow some kind of the formulation and by using your coordinate system, and you can positive and negative terms. I don't like to use this kind of strategy because sometimes different when I working with different axes, are especially to biaxial moment, formulation is not work efficiently. Always I am using the right hand rule, and compression tension description for me is better. Therefore, in whole example, I am following to the compression and tension directions. Okay, so you can see this is the compression direction. I put to the negative. I've said the compression is negative, tension is positive in my side. Okay, if you don't like this symbolization, okay, you can use the reverse. It's up to you. Okay, I want to continue. To normal stress to bending moment, first of all, I want to start with the point B. The best thing in here, you can see, this is we move to do our system in the middle from to moment like this. Okay, this distance between this center of the cross section to B is, what is the value? 50 millimeter. Therefore, we call this symbolizes the y is the maximum value C. You remember the sigma is equal to m divided by y I times y. I use the C term instead of y because when the y is y maximum is equal to the C. Therefore, maybe in the book you remember that to my maximum is equal to C. This is also equal to 50. And I put the formulation sigma B bending. So I converted from Newton millimeter. This is the value of C millimeter. This is the moment of inertia. BH cube divided by 12. Maybe you have a trouble to, hocam, what is the B, what is the H? Maybe I can help you. This is direction is like this from right hand rule. Okay, put your 4 fingers to direction of these bending. Okay, your thumb finger, okay, showing this direction. Okay, and I want to use this direction as a X. Okay, so this direction should show Y. So for X direction, Y direction, from this definition, this term should be. Sorry, I have a trouble with my computer working so busy. Therefore, I have a trouble when I drawing something. This is B. Okay, this should be the height of beam. Okay, this is the width. This is the H. So B is equal to what is, I don't know, 40. Okay, H is equal to 100, like this. This is X, this is Y, this is 40, this is 100. Okay, this point B. Okay, this is the point C. Okay, so if I apply this, I obtain to do 11.25 megapascal tension. Why is the tension? And now you can see this direction is make a compression. Therefore, this area is the compression area. This is the negative. This area, they are pulling back to this area using right hand rule. This is the tension area. I am defining by using the way of the direction of the moment area. If your moment direction going to the, there make a pressure in here, compression in here. Therefore, this area have a compression side. Okay, this is the compression side. Sorry, hadi gözünü seveyim. Yep, this is the tension side. So point B is the tension part, point C is the compression part. Therefore I write for point B is as tension. For point C direction in point B and C, why the values is same, moment of inertia is same, moment is same. Therefore, the value is the same, but direction is compression. Therefore, I put the negative. So if I add these values, you can see I put the negative for compression, positive for tension for point B, 7.5 for tension at sigma B, and sigma C is equal to both is negative. Therefore, I've miswrite. It's not tension. Okay, this is compression and negative. Sorry, copy and paste error. Maybe I can correct it. I think that this one is better. And slideshow, discard. Where is it? My question solution in here. This is the compression negative. Okay. Save and continue. Okay, also graphical illustration available in here. You can see compression, tension for B side, compression C side. If I add, you can see B and C like this. Okay, also if you in some question, if you want to find the zero stress line, okay, there's a linear relation between two stress distribution, equality of the triangle. Maybe you can remember by using the equality of triangle, we can find to the zero stress zone. I think this solution is not written in the question, but if the question needs the zero stress point, okay, location of the zero stress point, this is easy. Okay, let me using this. For example, I say, I'm sorry, like this, this is the, this is tension side, sorry, tension going to do, tension going to do far from this surface, compression going to the surface. Therefore, I want to write like 7.5. This is the 15. Okay. This is relationship. I set the linear relationship. This is the x. This is the 100 minus x. So how we can find the x? X divided by 100 minus x is equal to 7.5 divided by 12. I'm sorry, not 12, 15. So this is equal to 0.5. So x is equal to 33.3, and like this, 33333. It's continuing like this. It's not complicated, it's very simple. Sometimes biaxial bending, there is not straight line. In surface we have a maybe different. Okay, never mind. I don't need to tell. You are not responsible. I don't want to confuse your brain anymore. It's okay. Also, this information is not needed in the question. This is the result. Therefore, I don't need to go in detail. Okay. Now we have a second question. It looks like it's very similar to the first question, but one more thing is a little bit different because there is not only one eccentricity to axial load position of the axial load is not middle of the side, is the corner. Therefore, two type eccentricity occur. The first time is like this. I don't know the x. For example, this is a x. Also, one more eccentricity, a y in here. Therefore, if I want to move to the center of the section, okay, we have two moments, moment x and moment y. Therefore, a little bit different. Biaxial bending occurred, in other words, in this question. Okay, how we can compute? I think that this is, I don't have enough space. I can use this part, okay. Just only I want to show the coordinate system. Okay, book says this part is the x direction. This one is the y direction. In order to obey to the book solutions, in order to compare our solutions with the book solution, therefore I need to obey to the book rules. So I want to use a different color. The blue color is okay. So this is the eccentricity x. Ax is equal to 0.4, okay, and This is the eccentricity y, eccentricity, oh, sorry, sorry, I made a mistake. Let me check the correct arrays. Let me give seconds to correct. I think it's C. Okay. Then this part is ay is equal to 0.2. So to eccentricity x happens to occur or causes to the moment y, eccentricity y causes to the moment x. You don't need to memorize because you can, maybe I can say moment x is equal to p times a y. Oh, I'm sorry, this is not my mistakes. You know, so many sub 2000 programs working in my computer, always opening and closing. Therefore, some kind of bad writings can occur when I working on this. Sorry about that. And my is equal to p times a x. You can memorize this formulation or you can use the right hand rule. Okay, you know, when you right hand rule, 4 fingers showing to the moment direction, and when you are 4 fingers showing the moment direction, your thumb finger direction of the moment. So for example, I'm using to do different color. For example, for t kilonewton, okay, for x-axis, okay, make a moment like this, okay, in this direction, okay, your thumb fingers, okay, like this, showing to the like this direction. I am using the two arrow meaning that the moment, okay, this is the my. How we can compute my? My is equal to, you know, this moment are responsible for ax. Therefore, my is equal to 40 times 0.4. This is equal to 60. Okay. And I want to use a different color in order to confuse. Let me wait a few seconds. Hadi gözünü seveyim. Lütfen yardımcı ol bana. Yeah, I want the dark mode. And also this moment make a moment like that direction. And also when I am using to the right hand, okay, my thumb finger, okay, showing to this direction, okay. This is the mx. How I can compute the mx? 40 times ay eccentricity. This is equal to 0.2 and mx is equal to 8. So if you don't like, okay, use the formulation. You can obtain, you can obtain same values. It's up to you, okay. I prefer to this strategy because I can have chance to see the whole moment directions. Okay, graphical illustration like this. Okay, now we obtain to the axial force, moment x and moment y. There is no shear force occurred on this system. We can also, there is no shear stress occurred on this cross section. Let's start to calculate the stresses separately. First of all, I want to start with the axial force. Okay, you know, axial force, we have the constant normal forces. We obtained the P times A formulation, and we obtained 125 kilopascal. You know, 40 kilonewton force down direction. It is the direction is going to the surface. Therefore, that's the compression side. Whole section, both point A, B, C, D have a same value compression. This is the 125. Therefore, I don't want to separate for point I is 125, point B like this, okay? For all points, for whole surface, okay, we have a same compression values. Okay, let's continue. Now I want to cause the normal stress due to the moment mx. You remember that this is the moment x. Okay, sorry, not moment x, moment y. I misread. Sorry. This is the moment x. You can see a moment x following to the direction of the arrow. This part is the compression part, okay. The other part is, this part is the tension, okay. If we consider just only moment x, okay, point B and C has on compression, point A and D is the tension. How I can understand? I am following to the arrow and pressing to do that side. The other side, they are pulling back, pulling up. Therefore, I am thinking, I decided, not I decided, I understand that point A and D side, like this area, this section, area of this section, part of this section is the tension side. This side is the compression side. So now I want to compute to do point A, B, C, D, whole of the part, but I don't need to compute all of them because, you know, this is the symmetric shape. Distance from the centroid of the point B and distance from the centroid of the section and point A have same value. This value is the, what is this? I think that 0.2. Therefore, I can write to do y is equal to 0.2 or C. Okay. C or y max is equal to 0.2. Therefore, I write to do m time mx. This is not cx. It should be cy, I think that. Yes. This is miswritten in here. Cy divided by ix is equal to 6 times 0.2 times moment of inertia. You know, from x-axis, this is the y-axis. So this should be b. Okay. This should be h. Therefore, b is equal to, let me check, x, y. So b should be 0.4. I'm sorry, sorry, I made a mistake. Yes, this is correct. Sorry that. Yes, I should erase. So b is a 0.8. Okay. H is 0.4. Okay. BH cube over 12. Okay. So m times cy times ix is equal to, if I use this formulation, where's the value? I miswrite. I think that I forgot this. Okay, let me correct it and show this part. Okay, where is it? My question solution. Yeah, this should be is equal to 375 kilopascal, like this. And also, I don't forget to correct this one. This should also Cy. Okay, let's continue to the next slide. Okay. Also on bending Y, we have a like this position, and this moment causes to do bending for Y bending, and you can see this arrow going showing to this side. Therefore, this is the compression side. Okay, and I can use different color. This green side is this is the tension side. Also, this system is a symmetric shape, therefore to C value is equal to you can see Cx is equal to like 0.4. So I can pass to the next slide. You can see 0.4 Cx, the moment and moment of inertia. You can see Ay is equal to b times, sorry, h times b cubed over 12. Therefore, I can write this is the h, this is the b, okay, h times b cubed divided by 12. So I forgot to write the result again. And in this card, also we obtain to do same value. This is equal to do, sorry about, I forgot to write the solution. 375 kilopascal. Also, don't forget to write the equality in here. Let me check. Yeah. Also, I already wrote in here. I have already written in here. Also, okay. So you remember that in here, point D and C is the compression side, point A and B is the tension side. I say, and also I write in here. Now I want to start. First of all, I want to start with the point A. You remember for axial force all over the system, we have a 125 compression. For compression, I want to put the negative. And first of all, I want to write the bending X. You remember for bending X, point A and D part, this part is the tension. Therefore, I write the positive. Sorry, I write the positive 375 kilopascal. Also for bending part, bending Y part, you can see bending Y part also similarly point A and B part. This part is the tension, so also point A has a tension part. Therefore, I have write the 375. We obtained the 625, not 600. This should be, yes, 625 kilopascal. This is the direction as the tension. For point B, axial force is same, 125 minus. Bending X is the, let me check to the bending X is equal to, in here, the compression side. Therefore, I write to the negative 175. For bending Y, in here you can see this part is the tension part. This is the 100 positive 375. This comes disappear, and we obtain to the minus 125 kilopascal. For point C, you can see for point C, I want to go in detail, and both end is compression. Also, we have a compression side, and we obtain to the minus 775 kilopascal. Point D is the reverse of to point B, and axial force is same, but for bending X, tension stress occur, tension normal stress occur. For bending Y, the compression stresses occur. Values is the same because this terms becomes disappear. So we obtain the minus 125 kilopascal. Also, graphical illustration. I say this part is the bending moment, x-axis. This part is the tension part. This is the compression part. This one is the tension part. This is the compression part. You can easily see. Also, some term is also, where is the one picture is missing? Okay, I think this is enough for this week. Okay. Also, solution of the example 7.3 available in the slide. Okay, you can check and you try to solve by yourself. Okay, if you have any question, please you can ask on the Teams platform as a comment. Okay, solution of two example 7.4 and 7.5 is missing. If I have time after chatting platform, okay, I am trying to solve one of these question. Okay, the next remaining question, another question, you are responsible yourself. Okay, also if you know this solution of books is taken from the Beer and Johnson, maybe you can look at the book and you can find the solution of the both examples. Okay, I think this is enough for first week. Okay, see you on Wednesday. Take care. Bye bye.